Okay, so before we go on to this example, you see that this is quite a big example because now it just gonna be a pretty good guideline for you to handle the design aspect of things. So let's us try to complete everything with this. So we're going back here to try to cover some ground on a few other issues left out of the flexural members. Okay. First is the weak axis bending. You can see that sometimes you may have the bending moment on the weak axis of the member. Let's say you're not going to use this member to carry the load like that because the load carrying capacity will be reduced dramatically simply because you are using the weak axis. However, that might be the case when you have a beam like this and then you have the load coming in sideways to cause the bending in the weak axis, okay? Because that is your weak axis, right? If the load coming to the side, you're going to have bending moment in that axis. Now, when you look at this, okay, because we know the stress is going to be like that, yielding of plastic, but right there in the web, stress is going to be 0, so the web will not buckle. So now we are left with just one thing to take care of. That is the flange local buckling. Okay, and now your nominal moment simply will become the yield stress multiplied by the plastic section modulus in y direction. Okay, now yeah, that's probably okay. That's a minor axis bending. Okay, now another issue. The first, we generally have two things in terms of design. First, what we have done so far is core strength, right? And we must make sure that our member can withstand the bending moment caused by the load. Another issue that comes with it is what we call serviceability. Well, the word sounds grand, but it certainly means that your beam should not have too much deflection. Okay, and we are going to always check this in the elastic behavior. Okay, because when we talk about the deflection, you don't want deflection to cause, say, some permanent damage in your member. You want to control whatever that is about the deflection to be in the elastic region. And therefore, we always, regardless of any of the design approach that you use, you always calculate your deflection by using service load. Okay, some seem to be making mistakes about this because when they use LFD, they just use the factored load. We always use service load. Okay, just a real load. Calculate the deflection and we keep it in the elastic limit. That means, your deflection is going to be some coefficient. They multiply by WL to the power of 4 over EI thing. Okay, so if it's a uniform load, your coefficient becomes 5 over 384, for example. Or if it's a point load in the middle, it's just going to be some coefficient PL cube over EI. So you can see that your deflection depends on the load, on the span length, and on the properties of your material and section. Now you see it doesn't have anything to do with plastic or anything. It's just the material property and it's just the moment of inertia. So if you cannot change the load or the span length and you're using steel, the only way to fight off the deflection is by choosing higher moment of inertia. That is why we have this table as not this one, that one. See, when say sometimes when you say you have a very long beam, a long span beam, so and the load is not that high, so the requirement for your plastic section modulus is also not very high, so you can pick up a small section. But because of the fact that your beam is long, you can look at this say formula. See, it's power 4 for the length. So you may have a serviceability issue. And when that's the case, you now start to have to pick up your beams by the moment of inertia instead of plastic section modulus. And then this table will become useful. Okay. Now, generally, this is done by some project specification. It's a rule of thumb. You will not see any, say some criteria written in AISC specification nor the EIT. Generally, it's based on experience and some specific requirements for each project. You may see something like L over 240, L over 360. This is, coming from the imperial unit. You can see that. Because that's they measure the length of the beam in feet and then deflection in inch. But they have a rule of thumb ratio to select the beam based on the deflection in inches. Okay. Now this becomes more universal. You may see L over 500, some number like this for maybe crane. If you use the steel beam to support the crane, you may have to limit the deflection to a very, very small number like this, because if your beam deflects down too much and it's sagging, your crane cannot move, right? If you cannot imagine this, just think about the moving crane in our lab. If the beam is sagging, is coming down like this, your crane is just gonna go down in the to the lowest point of your beam, and that is not nice. And this kind of limitation can be used to limit the vibration of the machine as well. When you need to design some floor or some, say, foundation for your equipment, you have to be concerned about the deflection, because if the deflection becomes too large, it will result in too much vibration for your machine. It becomes inoperable. Okay, classic example would be, if you can recall the stairs that you have at KFC, can you recall that? The stairs where you take to the second floor, you can get into CB3 building. That stairs vibrate a little bit, right? It must have been, the control of the deflection. And we may use this rule of thumb. They use that maybe if you consider the live load of your floor, the deflection due to live load alone should not exceed L over 360. And for a roof, the entire thing should not exceed L over 240. Okay, but remember that's empirical. Okay. Now, another issue where you can use to tackle the deflection problem is what we call pre-camber. Okay, that means you know how much your okay, bring this up a little bit. Let's say you know how much you can expect the deflection is going to be under the load. So when, let's say, that's due to, if it's a date load, say maybe, okay, I'm pretty sure about the date load. I can calculate deflection of my beam due to date load. It's going to be 2 centimeters, for example. I can put the pre-camber on the beam to, bend it so that it goes up 2 centimeters before you have date load. Okay. Now, when you install this, when you erect this beam into the system and the date load is fully applied, generally it should be the load from the floor and finishing, things like that. But when you have date load acting on this pre-camber will be equal to this, so they cancel each other out, and so now you have the beam level. Okay, so when the beam is level, the deflection that is going to occur afterward will be just due to live load alone. But that is pretty smart idea. Any question about this? But the pre-camber will come with some limitations as well. for example, because actually this picture is a bit optimistic, you know. Say the real beam, when you pre-camber it, you know, its end doesn't look straight like that. It's just going to look like that, right? So to try to connect this beam to the connection would be, say, challenging as well. Okay? Now, another thing that we should talk about is the shear strength of your member. Okay, so it's part of the strength that will be added up to the strength part. Okay, we have strength and then we have serviceability. The strength, now you have the bending, where you have to consider local buckling and then global. And now you're going to have shear. That's our next important thing. Well, generally, when we are dealing with steel beams, it's pretty bending dominant, and shear is not going to be as dominant an issue as the bending moment. But still, as good engineers, you need to be aware of the fact that your beams can fail under shear, and therefore you need to check it. Okay, now, wow, just look at this formula. Shear stress is equal to V over dW. Now, D is the entire depth, and TW is, of course, the width of your web. So we are talking about this as this area, right? D multiplied by TW. So whatever happens to your VQ over IB, man? Do you remember that? Do you remember your shear stress equal to VQ over IB? Why am I saying that I'm going to use this formula? You just listen without, you know, feeling what at all. So what's the point learning this formula? Huh? You have come across this formula in mechanics and materials, right?
Yes.
And why am I using this? Is the direct shear. It's just the force divided by the area. Do you know why? So quiet, right? You may wish to try your luck and then better not. So let's look at this. What would be the shear stress if I calculate the shear stress by using this formula? If I use this formula to calculate the shear stress and then I try to write the shear stress distribution of this beam, how would the shear distribution look like? Anyone? Extra credit if you get it right. And your generation should be able to get this right by just, you know, Google it, right? To Google something like this would be difficult. Huh? What would be the shear stress distribution of this beam? It is correct that this is your shear stress formula. And this is flexural shear. So this is your flexural member. So you should calculate the shear stress by using the flexural shear formula. Is that correct or not? Is that a correct idea? The shear in your beam is called flexural shear. It's the shear that caused by bending moment. Am I correct or not?
Yes.
Yes, it is. I am correct. So how come I say I can use this direct shear formula for my beam? So am I wrong here? But it's in the PowerPoint. It better be correct, right? Otherwise, I wouldn't put it on my slide. What's the big idea here? So what happens is this. If you use this formula, the pink one, to calculate the shear stress distribution of this beam, it's an ugly picture, will look like this. you know the maximum shear is in the centroid, right? So that's the maximum value. And so your shear stress will look like this. But then when you reach a flange, that's a sudden change in the B term, right? So B will change from T web to BF. So that means the stress drops down dramatically because the width is much larger, and then it goes down to 0. So that is your shear stress distribution in your flexural member. Meaning, you see, the majority of the stress is right here. And you can do some calculation, and then you will see that, you know, averages out. The 90% of the shear is carried by the web because the flanges are there to carry bending moment. So even though it is true that this formula is correct, but we can simplify that formula by simply using the direct shear without, you know, losing much. So the shear stress in your H shape will be calculated by using this. Okay, and the stress that occurs shall not exceed the shear yielding stress of steel. This is roughly the tensile stress divided by square root 3. That's von Mises criteria. And 1 over square root 3 is 0.57 something. So they don't bother, you know, because we are not scientists, we are engineers, and we approximate things. So we're not going to go crazy and use 0.57 something all the time. So let's say, okay, 0.6 is good enough. So you see, so for those of you who are crazy about significant figures, you're just going to go nuts here, right? And knowing that this is not the actual number, it's almost 0.6, but see, we can live with it. So therefore, from this, now the yield stress becomes simply 0.6 Fy multiplied by the area of the web. But this time it is this entire area. Okay, so simply the area of the web becomes the depth multiplied by the thickness of the web. All right, but still you can see in the sheet now saying, ooh, buckling needs to be considered. So this is the pure formula where buckling doesn't occur. So to consider buckling from this, we add another factor called CV. Okay, so the basic formula for the nominal shear is simply 0.6 Fy. Now you know where 0.6 come from. Multiply by the area and then multiply by some coefficient to account for the fact that your member under shear can also buckle. Okay, and yeah, this is a general reduction factor and the factor of safety. So I don't think you guys have any questions in this part, but you may in the next part. So now, they call it I shape, which means any shape that looks like an eye. But remember that the section that we use for hot roll in the market, they call it H. But H and I is pretty similar. They say I shape like this. That means this also includes the I girder and then the I beam that is built up section. Okay. Now, when the H over TW, see that? That's a slenderness ratio of your web, right? It's less than this limiting value. CV is 1, which means it doesn't matter if it's there or not because it's equal to 1. But in addition to that, if your web slenderness ratio is lower than this number, you see the phi becomes 1 and the factor of safety becomes 1.5. So how can we have something like that? Are we so sure about everything that we are not going to reduce anything at all? Now this one has history. Okay. Now remember, this is special case. I should write something down for you. Special case where, you know, the web slenderness ratio is so low, you may end up using this. Now, you know, I'm going to tell you a history of the design because I was there when this happens. In the old times, when the specification for steel had been developed and so, they began by using the factor of safety for shear equal to 1.5. Okay, this is in the beginning. It's like a prehistoric era. They begin with say prehistoric here, too much. But the first time that LIFD came out, because of the concept that, you know, you are going to use the full strength of your section, but you have to keep in mind that something bad may occur. Your section, maybe, how would you know that the thickness of the web is exactly like that? You know, maybe the error in the manufacturing process will give you the web that is slightly thinner than the number suggests. So they always reduce something. So in the beginning, in the prehistoric, this is 1.5, but then phi is 0.9. So you remember that we used to talk about the magic number in the beginning of the class, that ASD and LIFD must have a proper relationship. And the magic number that we use is 1.5 when the live load to dead load ratio does not exceed 3. And you always multiply the factor of safety and phi, you always get 1.5 because of that. So generally, when you have a factor of safety equal to 5/3, the phi is 0.9. So you multiply that, you always get 1.5, right? So now, for some reason, ASD in the old days, they use factor of safety for shear equal to 1.5. But then LIFD begin by using 0.9. So we are losing that relationship. They didn't know what to do except to change the phi equal to 1. So that the magic number is maintained. So that's why you have the factor of safety equal to 1.5 and then the phi without any reduction at all. But you can only use this when your H/TW is less than this value. Okay, they allow you a special case. Is there any question? Hello? Now, that is not normal. What is normal is this. Webs in general here. This is normal. This is a typical case. Now, they say you have to check your web slenderness ratio, but with this value, it looks more intimidating in a way, because it's not that one, but it's this one. But instead, you have KV, another value inside. Now, this is a universal formula. KV, for now, you don't have anything to do with it. Okay, so you can leave it here, but there's a note here saying that for typical beam, KV is equal to 5. So you can say that you can plug in KV equal to 5 here. But I prefer, oops, sorry. I prefer to include everything. So in the future, if you encounter a problem like this, you know what it is. KV will be different from 5 when you strengthen the web of your beam. Okay, just like reinforced concrete, where you can add the stirrups to increase the shear capacity of your shear, right? Of your beam, right? It's the same here. In the steel beam, sometimes, especially with the build-up section, you can add stiffener, just like adding the stirrup to your steel beam. When you add the stiffener like this, your K can be greater than 5. But for now, let's say any typical hot roll beam where we generally do not add the stiffeners to increase the shear strength, you can say KV is equal to 5. You can multiply this into this. And this limit come out to be around 2.45 square root E over Fy. Okay? Question? Yeah, that's what they've written there. That's how it is. So yeah, that's how it is. I try to simplify. But you know, after showing you this, I will add some more. Okay. Now let's try to understand this a little bit. So okay, you have oops. Let's say now you have, let's say this is the H over TW. Okay, you have 2.24 square root E over Fy, and then you have 2.45 square root E over Fy. Okay. Now, when you check your slenderness ratio and it is less than this, you may use phi equal to 1 and factor of safety equal to 1.5. Now, generally, when you look at the shear here, you can forget about that and use the typical one. It's not wrong. It's just slightly conservative. Okay. So from here, oops. There's this small zone here where you say this is phi is 0.9 and factor of safety is 5/3 as usual. Okay, so let's say if you check the slenderness ratio of your web and it is greater than 2.24 square root E over Fy, but not this, you have to use this phi 0.9 and factor of safety 5/3. If you check and the slenderness ratio of the web is less than this 2.24, you may use this, but you don't have to. You may stick with this. Nobody's going to say you're wrong. But that, you know, those factors are always correct. But when you are down, when you are lower than 2.24, you may use this. That's all. And one more thing, this is your limiting value. Here, CV is equal to 1 for all. And I can say that all the hot roll sections, both SS400 and SM520 have the H over TW less than 2.45 square root E over Fy. Okay, so yeah, it's safe to say that for all the hot roll sections, your nominal shear is simply 0.6 Fy dTW. Okay, but you always have to check this. Okay. Any question? Is there any question? Are you sure you get this? But the bottom line is that you can always, okay, I don't want to be bothered by this craziness around here. I can just stick with this. That's fine, you know. I'm not gonna say you're wrong. You can use this all the time as long as it's down here, right? The slenderness ratio of your web is less than this. Even it's greater than that, you can use this, but your CV must be calculated. That's all. So come back here. Generally, we are always here. For the hot roll section available for you, you are not going to get into this CV formula. You will encounter this with the build-up section, and you should, because let's say I don't know, because I hardly involved with the design of the build-up section in Thailand, and people would be afraid of the web local buckling, and they would just make sure that the web is thick enough to avoid all this. But what would happen would be, if you increase the web thickness so much, your beam will become very heavy. And you should know by now that the web does not contribute much in terms of flexural capacity. So it is not a wise choice to use the thick web simply to avoid the local buckling issue with the web, either with bending moment or this shear. That's why the the US engineers, they always have the issue with the slender web, because they want to use slender web. They want to reduce the weight of the beam, and then they will try to strengthen the web later on to make sure that they can carry the shear. They're not afraid to do this, and they've been doing this for like 100 years or so. So if you have the opportunity to design this one day, bless you, you may think that you're gonna let your beam web become slender, and then you're gonna strengthen it later. Believe me, because the web is pretty long, right? And it just constitutes the depth of your beam. So when you increase the thickness so large, it will increase the weight of the beam very significantly as well. So okay, now go through that. See that how crazy it is. So generally, we are always here. Okay. So that sums up everything. That's an issue that another failure in the beam where I will cover next time. So now, it's not here. I wrote it somewhere, but maybe here. The shear now will have the local issue to check, and then the say, I don't know how to call it, say shear capacity. Okay, so generally there are like 5 issues in all if you are going to design one beam. And if you go back and look at your rubric, should I show you a little bit here? Outcome rubric. When you design the flexural members, let's say if you carry out your flexural analysis correct, you get your right bending moment, you must identify design criteria correctly, and then failure modes. Now, in order to get this 10% and move on to level 4, you must, oops, that's the wrong one. That's the wrong one as well. Where is it? Oh, it's gone here. You must be able to identify that when you design the beam, you need to check these 5 things. Okay. So is there any question? there any question about the shear? If not, let us get into this design example where I created it especially for you to see how things go. So let's take a look at the plan in one way, okay? And this is going to be your filler beam or secondary beam, right? So in your design project, you're going to have your secondary beam that will support the say 4.5 meters long floor. And in this case, now I use the secondary beam. So this is going to be my tributary width, correct? 2 meters. You should be familiar with this by now from, you know, structural analysis and everything. Okay, and in this case, because this is the secondary beam that support the floor, so you can say that the floor helps brace the beam. Okay, so you can say your beam is laterally supported. Okay, so it is your job to identify all these loads that will be on your floor. So let's say, you know, for demonstration, say I'd say slab and deck, the weight is 200 kilograms per square meter. The finishing, say that's about the granite, maybe it's above 100, and miscellaneous, anything that I think may be put there by the architects, some piping system underneath, you know, piping is not that heavy, and some ceiling, insulation and stuff, that's 550, that would probably be okay. And then the live load. Okay, so in let's say if I'm going to use ASD, the total load here, it is 750 kilograms per square meter. Okay. Huh? Okay, so now say the W acting on this beam is going to be 750 multiplied by the tributary width 2, right? So that is 1500 kilogram per meter now, right? Because it becomes a uniform load. And say, I don't know how much my beam is going to weigh. And my, say, preferred number is, say, assume beam weight about 100 kilogram per meter. So, well, unlike the roof where purlins are generally pretty light, this beam, you may want to include the weight by assuming the number. And once you're done with your prelim design, you can come back and look at the section, whether or not it is far off this number. Okay, so now I can calculate my moment. My MA is simply going to be equal to 1600, right? Multiplied by 5 squared over 8. Right? Coming out, that is going to be and this is in, it's in meter, so it's 5,000 kilogram meter. So let's say if you look at the rubric, so many things I need to go through. So let's turn off something. Okay, maybe I need this. My C. How much? What is this? So let's take this out. And okay, now you see that would be the analysis, correct? What I just finished, that is the analysis here, level number 1. Oops. So you can say that this is level 1, 20%. Okay. And of course, it has to include the fact that you can, get the right load to act on your beam as well. So now it's the selection, right? Because I now know my MA. So from this, I can say first step is prelim design. So now I know that my MA cannot be greater than my nominal moment divided by factor of safety. Okay. Now that is also part of criteria. Oops. Let's get this out. That is your criteria. Okay. You know that you are going to use ASD, so you know you use your factor of safety. Okay. And now this is going to be equal to, because moment divided by 5/3, that's when you flipped it, it becomes 3/5, so it's 0.6 Fy. Okay, and then multiplied by plastic section modulus. Again, we assume that our section will be compact first, and then this is part of the criteria where, let's say if it's 400, this becomes 25. So that's say level 2, 10%. Okay, and from this we can get serious about calculation now. So you know that your Zx will have to be greater than your MA divided by 0.6 Fy. Okay, so now your MA is 5,000 kilogram meter multiplied by 100 to change the unit into kilogram centimeter. And now you have 0.6, and then you have Fy. Okay, that is 333. And so now you're here, it's time to enter the table and pick the section with the greater section modulus than this. Okay, so I think we are going to write something because we have a few minutes left. Or no, let's just leave it here. And let's say this is the end of the second session. Do you have any question? Hello?
Excuse me.
Yeah.
Since we would like to calculate the beam, right? But,
yes.
why do we need to? Yeah, that's mean the load that will apply for the load will acting on the beam will be the upper part, which is dead load and live load, right? And you draw become 1500, yes. Right?
Yes.
But I would like to know a little bit why we need to have the beam weight. in this situation because just only
Here, I have added it.
yeah.
So
I would like to know why we need to add.
Well, because the beam has a weight and it could be heavy, but let's say if you neglect this, it would not hurt much. But you know, it's there. And from time to time, if it depends on so many things. If the load here is very large, like say it becomes like 3,000 kilogram per meter, I wouldn't worry about the weight of the beam much. But it's there. So for those of you who like, you know, your design to be kind of a complete and includes everything, you know, you better include that. Okay, but say when I don't bother about the purlins and the truss because, you know, if you just look at some sections, you know that it's like 10 kilogram per meter. 10 kilogram per meter. 1 meter long, it weighs only 10 kilogram. You can just put it on your shoulder and just go back home with it, right?
Yeah.
But now this is 100 because this is a steel section now, and you carry the floor. It's the weight is much more significant. So you may want to include that. But let me tell you this now. I was becoming a steel folk when I was doing my degree, and then when I was taking the pre-stressed concrete class, I completely forgot to include the weight of the concrete beam. And when you talk about the weight of the concrete beam, it's not going to be this light, you know. That is like even less than 10%, like 5% of the weight. But the weight of the concrete beam could be as much as like 30-40% of the entire load that you are designed for. In other words, the concrete beam will have to support itself before anything, right? And because I was doing this steel so much that I forgot to include the self weight or concrete stuff. So that's kind of not nice. Okay, maybe.
Yeah. Could I ask more?
Go on, please.
Okay. As I mentioned, I just think about the primary beam. When we need to calculate the primary beam, that's for sure that the beam weight is also calculated, right? But in this case, will be the secondary beam. So I just think only the load will acting on the beam, and that means beam need to have behavior to resist any load that we use. But the thing is, we need to combine the load of the beam and the weight of the beam all case, right? All the time.
Yeah, you should. It doesn't hurt to include it, right? Why would you want to exclude it?
Yeah. I just think about this why we need to include. For example, like just we will consider only the selection of the secondary beam. Yeah.
You see, you know, you see when the calculation is complete, how much the beam weight will affect the entire design, you know.
Yeah.
But as I say, sometimes if you're not aware of this and you're so used to not including it, and when you have a big beam, it's gonna cause you some trouble. Like truss tube. I'm telling you, you don't have to consider the weight of the truss members in your project because it's going to be very light. But let's say in the future you design a mega truss and you don't include the weight, that's going to be some. It's your judgment as well, because the weight is real, correct?
Yeah.
It is. So to include the weight in your design is doing things realistically, so to speak.
Okay.
But let's say for the truss case, for the purling case like that, say it's very, very light. So I don't bother with it, because if you really wish to include the weight of the truss member in your analysis, in your design, now you have to run the truss as the frame. Because the weight of your member is a uniform load. So there is no such thing as a perfect truss in the world. You always have bending moment and axial force in truss. But because the weight is so small, we can say we will neglect the bending moment in the truss, but it's there.
That means it depends, right?
Yeah. So you may think that, oh, this is too much for you. No, it's not. This is it. You know all you need to know now. Now you are gaining experience from your design project. And if you do it yourself, you do it yourself, you're going to learn a lot. And this will help you greatly when you go out there and do the real work. This is what we do, And now you see the load part is very, very important. More so than the analysis itself, Okay?
Yeah, okay, thank you very much.
No, you're welcome. More questions, maybe?
For me, no.
For you, no. For anyone else? Okay, guys, that's the end of the second session. This time it's recorded, it's nice.